Welcome back, future pilots. In the last lesson, we explored the layers of the atmosphere. Now it's time to focus on a key force that controls almost everything in aviation: pressure. From how we measure altitude to how weather behaves, pressure plays a major role in flight. So, what is atmospheric pressure? It's the force exerted by the weight of the air above at sea level. That's a lot of air pressing down. But as we go higher, there's less air above, so the pressure decreases. This simple idea has major implications for flying. At standard sea level, atmospheric pressure is 1013.25 hectopascals, or 29.92 inches of mercury. These numbers are the reference point for most aviation calculations, but real pressure conditions change constantly with weather, altitude, and temperature. Pilots work with three common pressure settings: QNH, QFE, and standard. QNH sets your altimeter to show height above sea level. QFE shows height above a specific airfield. Standard is used above transition altitude to maintain consistent flight levels. Let's break those down. With QNH, if you're on the ground, your altimeter shows the elevation of the airfield. With QFE, it shows zero on the airfield surface. Standard pressure is always 1013.25 HPA, used for high-altitude flying and flight level separation. Why does this matter? Because using the wrong setting can create dangerous altitude errors. Two aircraft flying with different settings might think they're separated, but actually be flying at the same height. That's why correct pressure settings are essential for safe airspace management. Let's talk altimeters. They work like barometers, sensing pressure to calculate altitude. As you climb and pressure drops, the altimeter shows you going higher, but it's only accurate if it's calibrated to the current pressure, usually QNH or QFE. Imagine flying with QNH set too low. Your altimeter shows you're higher than you really are. Dangerous near terrain. If it's set too high, it shows you too low. Bad for separation. Always check the pressure setting before departure and during approach. Now let's explore transition altitude. Below this level, you use QNH or QFE. Above it, everyone switches to standard pressure so that aircraft can fly at predefined flight levels like FL 100 or FL 350. This keeps things consistent in busy skies. In most countries, transition altitude is around 5,000 to 6,000 feet, but it can vary. Air traffic control will advise when to set standard. When descending, you'll be told to reset your altimeter to QNH so you can descend using true altitude. Next, let's connect pressure to weather. Low pressure systems usually bring clouds, rain, and unstable or high pressure systems bring calm, clear skies. Knowing how pressure systems work helps you anticipate conditions and read weather reports more effectively. Winds are also driven by pressure. Air moves from high to low pressure, but the Earth's rotation deflects that flow. This creates rotation wind patterns, clockwise around highs in the northern hemisphere, and counterclockwise around lows. You'll see pressure in METARs and TAFs. A measure that says a Q1010 means the local pressure is 1010 HPA. That's slightly lower than standard, so you'll need to adjust your altimeter accordingly. Always check this during pre-flight planning. Changes in pressure also affect aircraft performance. Lower pressure means less dense air, which reduces engine thrust and lift. On a hot, low-pressure day at a high-altitude airport, your aircraft will behave very differently than at sea level. This concept is called density altitude. It's a combination of pressure, altitude, and temperature that tells you how the aircraft will perform. High-density altitude equals reduced performance. It's like flying at a much higher altitude than your instruments show. You'll use performance charts to calculate takeoff distance, climb rate, and landing distance. These charts factor in pressure, temperature, elevation, and aircraft weight. It's critical to understand how pressure affects these numbers, especially in marginal conditions. Let's talk human performance. At high altitudes, there's less pressure and less oxygen. Without cabin pressurization or supplemental oxygen, pilots can experience hypoxia, a dangerous condition that affects thinking, vision, and coordination. Most aircraft cabins are pressurized to the equivalent of 6,000 to 8,000 feet. Above 10,000 feet in unpressurized aircraft, you're required to use oxygen after a certain period. Knowing how pressure affects your body is just as important as knowing how it affects your plane. So to recap, pressure affects altitude readings, aircraft performance, weather, and your own health. It's everywhere. And understanding how to read, set, and respond to it is a core pilot skill. Let's now explore altimeter errors. Point 1. Common issue is pressure error. If pressure drops and you don't reset your altimeter, it'll show incorrect height. Another is temperature error, which affects true altitude, especially in cold air. High to low, look out below. This phrase helps you remember. If you fly from high pressure to low pressure without adjusting your altimeter, you're actually flying lower than it shows, dangerous near obstacles or terrain. Likewise, air low to high, clear the sky. Flying from low pressure to high makes you appear lower than you are, less risky, but still important. These memory aids help you correct for pressure changes during flight transitions. Another key factor is pressure lapse rate, the rate at which pressure drops with altitude. Standard lapse rate is around 1 HPA per 30 feet. Knowing this helps estimate pressure altitude changes and set your instruments accurately. Now consider pressure gradients. A steep gradient, where pressure changes rapidly over distance, can cause strong winds. These gradients are easy to spot on weather charts, especially when isobays are close together. These strong winds affect crosswind landings, turbulence near fronts, and fuel planning on long flights. Understanding pressure gradients gives you an edge in interpreting forecast maps and making route adjustments. Let's look at how pressure works in cockpit systems. Pitot-static systems rely on outside pressure to calculate airspeed, altitude, and vertical speed. If pressure sensors are blocked or inaccurate, key flight instruments will give false readings. Pilots must always verify instrument behavior, especially in icing or contaminated air. That's why pre-flight checks include pitot heat and static port inspections. Pressure affects not just theory, but the practical safety of every flight. Now let's revisit standard pressure settings used at cruise. Using 1013.25 HPA keeps everyone aligned at known flight levels. This simplifies ATC separation and prevents misunderstandings between aircraft from different regions. In international flights, crews switch from local QNH to standard when climbing through the transition altitude. Then, during descent, ATC tells them when to reset back to local QNH, so their altitude reflects terrain again. Correct pressure setting is a checklist item before takeoff, level-offs, and approaches. Forgetting to update it is one of the most common pilot errors, yet one of the easiest to avoid with good habits. Always cross-check altimeter readings with airport elevation during engine start or taxi. Even a small discrepancy can be a clue that the pressure setting is off, or your instrument isn't calibrated properly. To wrap up, pressure is not just a number. It's a constant force shaping your altitude, your speed, your decisions, and your safety. Mastering how it works is a milestone in becoming a confident, competent pilot. In the next video, Pressure, Part 2, we'll dive deeper into altimetry, vertical navigation, and practical in-flight examples. Thanks for watching, and see you in the skies as we continue learning how to fly with pressure in mind.